Now it looks like you guys might be getting something that's right, but neither of you are drawing the Newman projection that matches this picture. So let's go through together how to draw the Newman projection for this picture. Let's go ahead and number our carbons here a little. Oh, well, I guess, who's the alpha carbon? Here's the alpha carbon. I guess there's another issue here. There really are two different beta carbons. But I don't want to get into that right now because you don't need to worry about that in this part of the course. Maybe instead of calling this a methyl, let's call this a deuterium. So you guys are expected to know that a capital D stands for deuterium. That's just an isotope of hydrogen. So let's change this to a deuterium. All right, so this is just an isotope of hydrogen. This then would be our beta carbon. All right, so now drawing the Newman projection. So remember that in the Newman projection, you start with a dot and a circle. The dot represents one of the atoms and the circle represents another. Who does this dot represent in our situation here? The beta carbon. The dot is the carbon that's closer to the I. Well, this carbon is closer to the I, so we could label this as the beta carbon. And then what's the circle represent? The circle represents our alpha carbon. So here's the circle. The circle represents the carbon that's behind the carbon that's closer to your I. So that would be our alpha carbon. Okay, now where would this hydrogen be from this person's point of view? Wouldn't this hydrogen look like it was pointing straight down from the beta carbon? Okay, and it looked to me like from you guys' pictures, it didn't look like you were ending up with that in your picture. So you guys might have been drawing acceptable Newman diagrams if you rotated them, but it's best to have your picture match the diagram that we have on the board. Okay, so the hydrogen would be pointing straight down. So you actually want to draw what would this look like from the perspective of this I. All right, and now how about this methyl group? Well, obviously this is going to be pointing up, but it's not going to be pointing straight up. From this person's perspective, is it pointing left or right? Right, because if you're in the blackboard, the methyl group is on this side of the blackboard, to your right. So here's our methyl group. And then the ethyl group is behind the board. Well, that would be to this person's left. Behind the board is to this person's left, so we can put our ethyl group out here. Okay. All right, and now we can start putting substituents on the alpha carbon. Let's see, so where would I draw this iodide?
Straight down.
Yeah, straight down. Technically, it should be hidden by the hydrogen, but the convention is to draw it a little bit to the side of the hydrogen. So I'll put this over here. This really represents someone who's right behind the hydrogen, but we drew it a little bit askew so we could see both of them. And then we have to put in this hydrogen.
That would be to the right?
Yeah, in front of the board, again, is to the I's right, in front of the board. So the hydrogen would be over here, a little bit askew from this methyl, so you can see both of them. And then the deuterium is behind the blackboard, which is to your left, if you're in the plane of the board. So we put the deuterium over here. So this is a good systematic method for drawing Newman projections. Now, I guess you guys were tested on Newman projections on the first midterm. You were not going to be tested on Newman projections directly anymore, but you need to use them now in order to solve problems. So if you had trouble with this, you should go back and practice some Newman projections so you can do this quickly. It always helps to actually draw the eye and the direction that the eye is looking when you're doing this. Okay. Here we have, say, our base. Now, what's the base going to do? Remember that the base is going to steal a proton from the beta hydrogen. So as the base wants to do this. And remember that simultaneously, this leaving group is going to be leaving. You can't actually show the other arrow here because the other bond is inside the board, so we can't show all the arrows. Maybe I shouldn't even bother with the arrows here, but here's a couple of the arrows that would be happening. Now, does it look like this is going to be easy for the base to come here, or is there going to be steric hindrance?
Easy.
Is there any steric hindrance here? I know I said that steric hindrance wasn't a big problem for E2, but if it was, would there be any steric hindrance that would get in the way of this base coming in over here? Well, notice that the leaving group is kind of in the same exact position as this hydrogen is over here. The leaving group is in the same position as this hydrogen. So this leaving group can get in the way over here. This leaving group can get in the way. All right, so here's where things get a little bit subtle. What I said before was a little bit oversimplified. I said, or actually it wasn't oversimplified, but I didn't explain it fully. I said before that steric hindrance is not a big obstacle to E2, and that's true. It's not a big obstacle, but it is a mild obstacle to E2. Steric hindrance still can be a factor for E2. So you just have to know when it is a factor and when it isn't a factor. Well, first of all, it's not a factor in terms of whether you got a primary, secondary, or tertiary substrate. If you look at the handout at the bottom of page 3, you can see that you can do an E2 for even a tertiary substrate. In fact, we oftentimes do E2 for a tertiary substrate. Down here, we got lots of E2s when we're working with a tertiary substrate. So that's a respect in which steric hindrance is not really an issue. That kind of steric hindrance, we can still do E2, because the steric hindrance would be even worse for SN2. So E2 is all we have left. However, steric hindrance is enough of an obstacle that we can't do the E2 like this. We can't do the E2 when the leaving group is blocking the hydrogen over here. So what we need to do is we need to rotate the molecule until it's in the anti-periplanar condition. We need to rotate the molecule until it's anti-periplanar. That's a term that you might have seen. Anti-periplanar. Anti-periplanar. In particular, we have to rotate the leaving group until it's anti-periplanar to the beta hydrogen. We need to rotate the leaving group until it's anti-periplanar to the beta hydrogen. Rotate the leaving group until it's anti-periplanar to the beta hydrogen. Okay. Now actually, you can either rotate the leaving group so it's anti-periplanar to the beta hydrogen, or you can rotate the beta hydrogen until it's anti-periplanar to the leaving group. You can rotate whichever one you like. It doesn't really matter. So I don't know, I guess it's going to be easier here to rotate the leaving group. So I'll leave the hydrogen where it was. So here we have hydrogen, methyl. So we're not going to rotate the beta carbon, but we're going to rotate the alpha carbon until the leaving group is anti-periplanar to the beta hydrogen. So where should I put the leaving group now?
Straight up.
Straight up. This is what you learned to call anti for the first midterm. In the first midterm, you learned about anti and gauche and eclipsed. So you can see here, there's tons of steric hindrance here because the iodide is eclipsing the beta hydrogen. We know that's the most strange situation where the iodide is eclipsing the beta hydrogen. Gauche would be better, but the best would be if the leaving group is anti to the beta hydrogen. So that's where the anti in this term comes in, over here. So again, we're really using some of the techniques from the last midterm. So we put the iodine here, and then obviously we'll have two substituents here. We have to decide, so remember that the other two substituents are the deuterium and the hydrogen. So you have to think about, if we rotate the iodide, where will the deuterium and the hydrogen end up? So where's the deuterium going to end up? Sorry?
On the right.
Deuterium?
Yeah.
Yeah, and the hydrogen. I don't think it's too hard to imagine like rotating this like a wheel. And if we rotated this like a wheel, basically we're rotating it 180 degrees. Well, if we rotated that back wheel 180 degrees, the hydrogen would end up on the left and the deuterium would end up on the right. Okay, and we know we can do that because we're just rotating around this single bond. There's free rotation around this single bond. Notice that the single bond isn't drawn. This single bond is between the alpha and the beta carbons is not drawn in the Newman projection, because it's in the plane of the board. It's the bond between the dot and the circle, so you can't draw that dot.
So in the second language book, there was like a problem I got confused about, and I think because it had multiple carbons, so you only focus on the alpha and beta carbons, right?
That's right.
Okay, that makes more sense.
That's right. So again, it's going to be helpful as usual to keep labeling the alpha and the beta carbons. Everything else we treat as a substituent on them. So those are the things that go on the spokes of the Newman projection. Okay. So now we have this anti, all right, and now we have the minimum steric hindrance. So again, the key thing is steric hindrance is not a big obstacle to E2, but it's still better to minimize it if you can. Well, here it's very easy to minimize it because there's free rotation around this single bond. So even though it's not a huge deal, it's big enough that the reaction is going to wait until we've got this anti-periplanar transition state. All right, and now we can do the reaction. I'm actually not going to try drawing the electron pushing arrows here because you can't show all of them because there's a bond that's hidden. So let's just do that over here. So this would happen like this, and like this, and like this. Now this is a little misleading because remember, the reaction won't really happen while the molecule is eclipsed like this. First it would rotate. But anyway, the arrows show the movement of the electrons. So the arrows here are still showing the movement of the electrons, even though the hydrogen would have to rotate before we can really do the reaction here.